Hello everybody, welcome back to high school tutoring. I'm your host Manny, and today we're going to be learning about free body diagram equations. So basically these are just going to be kind of like free body diagrams, but it's kind of like solving them. So the idea of today is to be able to do this, is find this value. So you see we have a free body diagram where it's accelerating to the right, it's got a frictional force, it's got a normal gravitational force. We need to be able to identify what place is positive, what's negative. So in this case, down is positive and then to the right is positive. So we're doing these separately. That's the idea. The horizontal separate from the vertical and the vertical separate from the horizontal. So here's what it would be. So these two would cancel out in this scenario, so that would be just 0. This is net force representing, so this F value. And otherwise, all we gotta do is just plug in these values, or plug in these two. So that means our gravity value and our normal value are subtracted from each other, and since they're equal 0, it will just be F normal is equal to F gravity. So the vertical, my apologies, the vertical makes sense. And for the horizontal, there we go. So this is just another way of saying net force. I actually forgot exactly what the term was, but I'll probably just have it in like a card or something here. And we can see that the right is positive from this little thing, and obviously the rule is that whichever one has a higher force value, or whichever direction the net force is, that's the positive. So you see our applied force is like the arrow is bigger than our frictional force, so we can infer that positive should be right, and it would equal mass times acceleration. And so otherwise, just plugging in for our net force, that means our applied force is subtracted from our frictional force, and it will be equal mass times acceleration. So that's an example where we have an object that's accelerating in either direction with friction. So here's some extra examples. So we're looking here at a push-pull with friction at rest or constant speed. So this time it's like this, but it's not accelerating. So we're taking a look here. Net force of the vertical, that bottom is going to be positive, and that means that normal force and mg is going to be what we're using because it's the same as the force of gravity. It's just mass times gravity. That's all it is. So we're looking at it here. That means that if mass times gravity, or the force of gravity, is the positive because it's like pulling downwards, that means that our equation is going to be mg minus fn is equal to 0, because we're just plugging into the net force. Which also means we can just add Fn like we did over here, and that would mean mg is equal to Fn. That's it for the vertical. So now if we're going to look at the horizontal, positive is going to be to the right for us. So that's how this is going to work. It's also down here. So we can infer from that this is our tension force, and this is our friction. So if they're opposing each other, we can just, and if it's equal to 0, that means all we have to do, and since tension force is going to be positive, frictional force is going to be positive, that means that we can just do, we should just be able to do this. We should just be able to do friction, so F of F minus T of F is equal to 0. Then we'll add tension force to the other side, and that means the friction force, or F of F, is equal to T of F, the force of tension. That's all it is. So that is our first example. So there's that. And we have push-pull frictionless accelerating. So in our scenarios, if we use like a hockey, like an ice rink or something like that, it would generally be frictionless. But that's not obviously real physics. It'll always have friction. So here we go. So again, we have mass times gravity, and we have the normal force. Again, mass times gravity is positive, so you can just copy what we had on the first one. Mg minus Fn is equal to 0, and then that'd be Mg is equal to Fn, just like this side. So there you go. I don't know why it looks like a D, but it looks more like a sword even. So now let's take a look at this. The horizontal right is positive because it is being pushed, which means that that value is always going to be positive because there's the net force is going to the right, so positive is going to the right. Otherwise, opposite direction, if it was going to the left, positive would be to the left. So that's how that works. So we're looking at it here. So we have our net force is equal to ma. So since we only have the force, like our actual push force, we just need to do F is equal to ma. That is it. Because net force is just all the forces added together. So these two, there's nothing opposing it. So it's just this force. So F equals ma. That is all. So hanging object at rest or constant speed. So we're looking at this here, and we're looking at force of tension is, instead of our normal force, we have a tension force that's going against the force of gravity, and it's going up. So we can assume there's no horizontal force on these, so that's good for us. But we can assume, since it's going up, that tension is going to be subtracted by mass times gravity, which is equal to 0, and then plus mg, and then that means mass times gravity is that. So that just means tension is equal to mg. That's it. So let's take a look at this other one. Now this time it's going to be mg minus t, because tension is not the negative value, and that's also equal to 0. And so we just have t equals mg. That's it for this video, realistically. Another thing that I want to explain really quick is how we get these values. You see, there's like, these values are all like, oh wait, that's not right. You see, we have the plus minuses, and we also, yeah, like this bit. How we find that? So I explained earlier how if the force, the net force, whatever direction that's facing, mostly for the horizontal, but it applies for the vertical, that will always be the positive direction. So you see here, especially in this example, it's positive to the right because the force is acting the most to the right. So, and when it comes to equal balanced forces, so you could see mass times gravity and normal force, we just go way down. You can choose either one. So normal force could be up, and then it could be up or it could be down. It just means that all these two forces have to be balanced at all times. If whichever side is accelerating, that's where it is. Again, these same scenario, these two forces are balanced according to what we've put here. So that is exactly what it is. So yeah, we're not using any values. We could, but I mean, it's a very long process and it's kind of annoying. So that's kind of it for this video, and I hope you guys enjoyed it and also maybe learned a little bit of a thing or two. And I will see you guys in the next one. Bye bye.